who foolishly attempt to say something about the proof and thus regret my life. All right, so here we go. Extension K equals to F, join the nth root of A, right, is Galois over F. Y, since it splits, x to the n minus a, right? So x to the n, this is basically that test problem you had, by the way. So this is x minus the nth root of a times x minus, let me call it omega, easier for me to write. Omega nth root of a, x minus omega to the n minus 1 nth root of a, right? Where omega, to the n is equal to 1. So I'm using omega for the nth root of unity, the principal nth root of unity. So it's a splitting field, therefore it's Galois. He says for any sigma in the if sigma in the Galois group of K over F, what do we say? Excuse me. Sigma of the nth root of A is another root of this polynomial. Right? Because we know that the automorphisms permute the roots, right? And so what that means then is that specifically sigma of the nth root of A, it has to be equal to like omega to some power, let's call it K, of the nth root of A, right? And that gives us a map from the Galois group to, he calls it mu n. I think mu n is the nth roots of, he says mu n denotes the group of the nth roots of unity. So his mapping between Galois K over F maps to, nth roots of unity, which he uses this notation. The mapping is sigma maps to, well, omega to the K. Well, I'm using a slightly different notation than him, but
I get
same idea.
Because omega to the K is 1, therefore sigma maps alpha to alphas.
He says, since F contains mu n, every nth root of unity is fixed by elements of the Galois group of K over F, hence sigma tau, sigma tau of the nth root of A. No, he's got a notation for this. He calls just this, I guess in my notation it would be omega sigma, omega sub sigma. That's the power of omega that you need to get. He's got zeta sub sigma, but it's the same idea, right? So then he's like, if you take sigma tau on the nth root of A, you get, sigma times omega tau nth root of A, which, again, omega t is a nth root of, this is a nth root of unity, but this is a F fixing automorphism of K, but omega t is an element of F by assumption here, which means we can pull omega t out of this F fixing automorphism. And then, of course, by notational, my notation, that's omega sigma of the nth root, times the nth root of A.
Which is just nth root of A.
which which is what he's written. And he says, well, since this, the nature of the field here means if you define the action, of an F-fixing automorphism of K on the generator nth root of A, that defines the mapping. So since this is equal to that for the nth root of A, it follows that sigma tau is equal to, omega sigma tau is equal to omega sigma, omega tau, omega sigma. I can't do it. Ah, son of a gun. Letters. Huh. Oh, well, these are numbers, so they commute, So, so this would be, omega sigma tau acting on the nth root of A, I guess, times nth root of A. Let me stop talking about this. So what he gets is omega sigma tau equals omega sigma omega tau, which shows you what? It's a homomorphism, right? Homomorphism. And what's the kernel?
Omega to the n.
He says the kernel consists omega to the n.
Or omega k.
Well, the question is this. So like this is let's say psi, right? Psi of sigma equals omega sub sigma, right?
Yeah. Well, anything. What maps to 1 would be all the omega powers that are equal to 1. They get you back to 1. Yeah.
Yeah.
Because you have where'd you write it?
In my k notation, it's going to be the k equals to. Oh, curses.
N minus 1. It's omega n minus 1. Like everything, all omegas that multiply together to get. You know what I'm saying?
Not yet. Just a second here. He says the kernel consists precisely of the automorphisms which fix the nth root of A. Kernel is
Yeah.
fix the nth root of A.
Yeah.
Okay, so the kernel. So we're
Because the kernel's things that map to 1, but in our thing, all the omegas that map.
yes, exactly.
All the multiplications of omegas that map into that give you back in the nth root of A.
Right. So this is a group.
Yes. Everything
And
that multiplies together.
so if this
1.
right. So this equals to 1 makes sigma in the kernel, right?
Yeah.
But how does that happen? You're saying that sigma has to be the what?
The w omega to n. Because we said, you see up here, it says it's Galwa over f, omega to the n is equal to 1.
Yeah.
So omega sigma is omega to the n.
Ah, yes. But it also has to be. So you said it has to be k equals n basically, right? So you're like, okay, so it's the sigma of the nth root of A equals to the omega to the n nth root of A, which is of course the nth root of A.
Yep.
So it's the one it's the identity.
Yeah.
So the point is the kernel is
But
the identity.
it can't just be that.
That is just that.
Also,
And
because you get omega n. So
because we set the isomorphism maps the identity, that forces omega sigma to be 1,
yeah.
which then by the definition of omega sigma, which is really up here, if this is 1, that forces this to map to that, which forces sigma to be the identity map. That's the only choice for sigma, is the identity map.
Well, okay. Essentially, what I'm saying is that if you, under group operations, you're going to have 2 omegas that multiply to get you omega sigma. So those aren't in the kernel also?
Kernel of 2 omegas that get you omega sigma.
Yeah,
No, there's just one omega that gets you omega sigma for a particular sigma that gives us a particular choice of k.
yeah.
And omega to the k is unique for k taken from 0, 1, 2, 3, all the way out to n minus 1. Now, if you're thinking about n, we shouldn't be, I mean, like,
Well,
this list, if we're going to put 1 here, we shouldn't put omega n over here, and vice versa, because that's the same element.
yeah. Well, isn't omega times omega n minus 1 equal to omega n?
Omega times omega n minus 1 equal to omega n, yes.
That's what I'm saying. So shouldn't that be in the kernel too, or am I?
No, because the kernel is the automorph sigmas,
Single elements?
the sigmas which map to 1.
Okay, but
Right?
the only one is omega sigma.
The only one which does that is the identity sigma.
Yeah.
The sigma which is defined by mapping the nth root of a to the nth root of a. So like, the point then is that, so this is, you know, psi is this mapping from here to there, right? And then the first isomorphism theorem tells us what? You can take the Galwa group, k over f, right? Mod by the kernel of psi, and that's going to be isomorphic to psi of the Galwa group of k over f, which of course is a subset, a subgroup of Sn. Well, Sn, yeah, Sn, nth degree. So he says this gives us an injection of the Galwa group k over f into the cyclic group. Oh, I'm an idiot, dummy. What was the image? I'm a dummy. What's the codomain of this homomorphism? Un, not Sn, dummy. Me, not you. Jeez. So what then? Oh, well then the thing is, mu n is a multiplicative cyclic group. So all subgroups of a cyclic group are cyclic,
Yeah.
which then proves that the Galois group is cyclic.
Yeah, we knew that.
Yeah. This Galois group is cyclic. Okay. Yeah.
Which, I mean, you know. Oh, but this is arbitrary. This is not, okay.
Yeah, there is an assumption that the characteristic doesn't divide n.
Yeah.
All right. Now, let's see here. Proposition 37 says any cyclic extension of degree n over a field f of characteristic not dividing n, which contains the nth roots of unity, is of the form f adjoin the nth root of a for some a. So basically, proposition 37 says, guess what? There's a converse, okay? Converse 30 says, proposition 37 basically says, hey, if you've got a cyclic extension, you know, a cyclic extension, then it is, with again, the condition characteristic of f does not divide n, then guess what? It is f adjoin the nth root of a for some a. That's what proposition 37 says. It says there's essentially a converse to proposition 36. And he also tells us that the two propositions above form part of what's referred to as Kummer theory. He says, let f be a field characteristic not dividing n, which contains the nth roots of unity. If we take elements a1 through ak in non-zero elements of the field, as in proposition 36, we can adjoin nth roots of these a1, a2, all the way out through ak, and that gives us an abelian extension of the field whose Galois group is of exponent n. And conversely, any abelian extension of exponent n is of this form. I don't want to get into all that. I'm just for your information, all right? And next definition here is where we need to get to. Ah, yes. Finally, the radicals. Definition. An element alpha, algebraic over F, can be expressed by radicals, all right, or solved for in terms of radicals. Why did I agree to write that out? Poor choices. If alpha is an element of a field K, obtained as follows. So F is K naught. That is a subset of K1. That is a subset of K2. And subset Ki, subset of Ki plus 1, subset of Ks equals to K.
This is kind of how we do the rationals and the reals, right?
It's like, well, what do you mean?
You know, like we have radical like root 2.
Ah.
Root 3.
But root 2 and root 3, they don't nest, yeah?
Oh.
So Ki plus 1 is equal to Ki extended by the nth root. Excuse me, it's worse than that. Son of a gun. I gotta put a subindex on that n. It's not the same n at every step. All right, we allow for the n to be varying n sub I, the n sub ith root of a sub I for some a sub I where? Well, a sub I in Ki. For I equals to 0 to s minus 1. And he says here, the n sub I,
Wait, but we can't divide F.
so the question is, what's this notation mean? Here, the n sub ith root of a sub I denotes a solution to x to the n sub I minus a sub I equal to 0. Okay. Let that be understood. He says such a field K will be called a root extension of F. Root extension of F. And this is all part 1 of the definition, okay. What's part 2 of the definition? Part 2 of the definition is a polynomial f of x can be solved by radicals. Solved by radicals if all its roots can be solved for in terms of radicals. All right.
I'm not sure how this proves that 17 gone is constructible. But
Yeah. Yeah, we're getting there. Brings us to lemma 38. This is on page 628, if you're keeping track. 628 of Dummett and Foote, 3rd edition. If alpha is contained in a root extension of K, rather, if alpha is an element of K, a root extension he says as in 21. I think 21 is, let me give this thing a name here. Star. Yeah, as in star. All right. Then alpha is contained in a root extension which is Galois over F. And where each ki plus 1 over ki is a cyclic extension, is cyclic. So let me kind of just sketch the proof for you here of this. All right. So basically, the proof is something like you're given star, right? And so the trouble is you can't quite use the thing I erased because you don't have nth roots of unity, right? But there's a couple different things you got to go on. The one thing is earlier in the chapter, he's explained that there exists this thing called the Galwa Closure, right? So you can appeal to the Galwa Closure, like K can be extended to its Galwa Closure, right? And then you can also take this K thing and multiply it by, you can multiply it by the nth roots of unity. So you can adjoin nth roots of unity by multiplying by the set of nth roots of unity through a construction in a section we skipped about the like multiplying two fields, K1 times K2 is a field. And that multiplication of fields plays nice with Galois extensions. So the ultimate result of putting all those ideas together is this lemma. No, it's like I think it's I'm pretty sure, like, for example, I don't know. I mean, so I feel like if you took this, for example, I think it is literally just the biquadratic field, for example. Like the product of these two fields gives you that. I can give you the careful definition. It's back in section such and so forth, but it'll distract me. So, but anyway, the details of lemma 38, they're on page 628. But that's kind of an overarching sketch of it, which is that there is something called a Galwa Closure. You can find all of this in there, and or maybe he first adjoins the nth roots, and then that gives him something that then you can take the Galwa extension of that, and then you've got something that's Galwa, and you've got something that has the nth roots of unity, which means then proposition, what was it? What's the number on that thing? A cyclic, the proposition, where'd you go? I think it's proposition 36 that we did earlier. So we'd have a field of characteristic not dividing n, which contains the nth roots of unity, and we would have an extension f adjoining the nth roots of a. So we would have that cyclic of degree n. And then to get I gotta stop talking. Okay, so it's lemma 38. And then that brings us to yet another definition. What's a finite group? Well, you know what a finite group is. A finite group is, it's right, is solvable, all right, solvable if there exists chain of subgroups one equal to GS, which is a subgroup of GS minus 1, subgroup subgroup G0 equal to G, such that GI mod GI plus 1 is cyclic for I equals to 0, 1, S minus 1. And so we have proved, quote unquote we have proved that subgroups and quotient groups of solvable groups are solvable. And if H is a subgroup of G and the quotient of G by H are both solvable, then G is solvable. So those will be some good homework problems for us to work through, I think, Audric. If I haven't put those in the homework yet, I should. I should replace the homework. I should replace some ugly technical homework I've given you with that, because that would be probably a use. These are all good claims to work out right here. But let's not lose sight of the goal here for today. We are almost there. That's right. So look at lemma 38. Look at that definition, and what do we have? We have theorem 39. A polynomial f of x can be solved by radicals if and only if its Galois group is a solvable group. That's the main event right there. Theorem 39. A polynomial f of x can be solved by radicals if and only if the Galois group of f of x is solvable. Now, if you're an outsider to this world, it seems like you're just saying the same thing twice, but you understand that that's not, we're saying something quite fascinating. I mean, so f of x being solved by radicals is talking about a tower of extension fields where each step we're joining a new square root or cube root or fifth root or whatever. Roots of roots of roots of roots. On the flip side of things, the Galois group being solvable, you're talking about a chain of subgroups, right?
Yeah.
So that's a statement in some sense about field theory. That's a statement in some sense about group theory.
Yeah.
And this is saying that they're interlinked.
Yeah.
So, yeah, and the proof, of course, is on page 628 to 629. Corollary 40. Corollary 40, if I'll fit it in here somewhere. Corollary 40, what does it say? The quintic. Yeah, exactly. It says the degree of equation, the general equation of degree n cannot be solved by radicals. The general f of x equals to 0 equation, right? Cannot be solved. By radicals for n greater than or equal to 5. So of course we have a general quadratic equation, right? And so so basically to prove that this is the case, all you have to do is to exhibit a fifth order polynomial which has what? A Galwa group, which is not what? Which is not solvable.
No, but that makes sense because once you get past 4, like 4 has, like, you can build a general 4, a degree 4 polynomial from 3 and 2 and 1, which are all solvable. But if 5's not solvable, that means you can't build like 6.
Oh, yeah, yeah,
So
yeah.
but all you have to do is prove 5's not solvable because like my first question was how does that imply 6 isn't solvable?
That's a good question. I've been in this for too long. I've forgotten about that question. That's a good question to ask.
No, but it makes sense because 5, you can, like, the general, any quadratic would have to, there's some 6-degree polynomial that's built from a 5.
See, here's the
And 5 is solvable at all.
so the general f of x cannot be solved by radicals for n greater than 5. Here's the proof. This also answers the question that you asked earlier today, which is what was the deal with all that symmetric stuff? All right, here it is. So for n greater than or equal to 5, the group Sn is not solvable. This is from chapter 4 in Dummett and Foote, okay? And hence, remember the Galwa group of the general polynomial was Sn, right? It's not solvable. Which then, of course, says that f of x not solved by radicals, right? And here I'm referring, the f of x I'm talking about right now is that general f of x we talked about at the start of today. Okay? So help me if my battery is out on my mic. I'm going to scream. La la la. Okay. Phew. That's a relief. But he says, to give an example of a specific polynomial over Q of degree 5 whose roots cannot be expressed in terms of radicals, we must demonstrate a polynomial of degree 5 with rational coefficients having S5 or A5, which is not solvable as Galwa group. So here's his example. We have f of x equals to x to the 5th. Now, I realize minus 6x plus 3, like the group theory I'm referring to here, I know you don't know. It's understandable. And that's, something we can try to fix a little bit. But okay, so one of the things I'm planning to do with the Audric is to like go back and do some of the group action stuff, because I know you didn't see group actions, right?
Yeah, I was gonna go, or like this summer I kind of planned on going through dumb and input, like you know how you have a guide to Gamelin? Like I was just gonna kind of do that type of thing.
Yeah, there's this crazy project guy who's trying to solve all the problems in dumb and foot. It's like, I don't know. It's,
I don't know if I'll do all that.
it's a lot. It's a lot.
I just feel like if I can teach a thing,
Mm-hmm.
I'll probably know it pretty well.
This is true. Let's see here. So this is a polynomial in Q of x, all right? I mean, obviously it's got rational coefficients, right? He points out that f of x, it's irreducible over Q by P equals to 3 Eisenstein. Okay, I think I believe that. Point number one. So the splitting field for this polynomial has degree divisible by 5. So all right. Okay. He says, since adjoining one root of f of x to q generates an extension of degree 5, right? He says, the Galwa group is therefore a subgroup of S5 of order divisible by 5. So let me say G is equal to the Galwa group of f of x, right? So we have G is a subgroup of S5, and the order of G, S5 divides the order of G, right? That means that there exists a 5 cycle in G. So he says the only elements in S5, well, he's the only elements in S5 of order 5 are 5 cycles. So G contains a 5 cycle. So like, just for the sake of making that not so abstract, that's something like 1, 2, 3, 4, 5. 1 goes to 2, 2 goes to 3, 4 goes to 5, 5 goes to 1. And we're, of course, as usual, using that as a notation for the isomorphism that permutes the roots that have been enumerated 1 through 5. They're 5 because it's a 5th degree polynomial. All right. Now, he does some sneaky analysis stuff. All right. So
Why does it start with -2?
aha. So f of, let's see, you read it out for me. F minus 2 equals what?
-17.
Uh-huh.
0 equals 3. F of 1 equals to -2. And f of 2
F of 1 equals what?
-2.
Uh-huh.
F of 2 equals 23. You see that from f of x has a real root in each of the intervals, -2 to 0, 0 to 1, 1 to 2.
Uh-huh.
By the mean value theorem, if there were 4 real roots and the derivative f of x equal to 5x to the 4th minus 6 would have at least 3 real zeros.
All right, hold on there, hold on. One thing at a time, one thing at a time. So this says IVT, there exists, 0 for f of x. Let's say, let me use letters. So IVT says there exists, let's say alpha 1, an element of, -2 to 0, such that what? Such that f of alpha 1 equal to 0, right? And the second two things says, the mean value theorem says there exists alpha 2 in 1 to 2, such that f of alpha 2 equal to 0. All right. And then you're like, now he's saying something about that mean value theorem, right? Another thing. Woe to the Calculus 1's class where I decide to judge their grade on the basis of their understanding of the mean value theorem. woe to them. Let's see, your f prime of x. so mean value theorem. Like any other theorem in Calculus 1 is widely unappreciated. F prime of x is 5x to the fourth minus 6, right? Now what's he say? He says if there were 4 real roots, then this derivative would have what? At least 3 zeros. Do you understand that? So think about this. If you have 4 roots, right? If you have f of x is the product I equals, 1 to 4 of, say, x minus alpha I. If that, let's say g, f is, I got a different meaning here, right? So g like that, right? Then you do g prime. It's what is it? It's the sum j equals 1 to 4 of, x minus, son of a gun, the product I equals 1 to 4 of x. Oh, I can't write this out. Stink. Let's see here if I can make this easier. If I had g of x is x times x minus 1 times x minus 2 times x minus 3, right? And I calculate g prime of that, I get x minus 1. Well, let me make it simpler. What are we trying to argue? This has what? At most what?
That can either have 4 reals, 4 complex, or 2 and 2, right?
Well, he's picking at if there were 4 real roots of then the derivative would have at least 3 real zeros.
Which it doesn't, because you can't have, you either have all 4 real or 2 and 2.
Let's see, roots. It would be like this one, this one, this one, this one, right? And so it has to look something like, it can look like a lot of different things, but the point is to turn around to get to the next one, right? So there has to be, if there's 4 zeros, that implies at most 3 turning points, right? So, but the thing is, this is, would you tell me f prime, our f prime is what? How many zeros are there for this one?
How many real zeros?
Yeah.
You can either have all 4 real, all 4 complex, or 2 and 2, right?
No. This specific example, when is that 0?
Oh, so plus 6 divided by 5 to the 4th. X is equal, when x is equal to root 4, 6 over 5.
Yeah, we got x to the 4th is equal to 6 over 5, right? So,
Roots of 6 and 4th roots of 5.
yeah, so x equal to plus or minus the 4th root of 6 over 5, right? So there are 2, just 2. Two real solutions there, which means what? We cannot have 4 real zeros.
3 root zeros. So you need 3.
No, we cannot have 4 real zeros of the original function.
Oh, yeah.
Because there are not 3 zeros of the derivative.
Yeah.
What does that mean? That means, continuing with our counting, okay. Hence, these are the only real roots. So the only real roots are this alpha 1 and alpha 2. Let's see here.
So
Oh, wait a minute, I missed one. There's also a 0 between a minus 2 to 0 and 1 to 2. I missed the 0 to 1. Oh, duh. Look, I'm an idiot. Look, this is right here, right? This means that IVT, there exists alpha 3 in 0 to 1, because it changes sign there, doesn't it? Right?
Yeah.
It's just right in front of me. I just didn't see it. I'm an idiot. Okay, so we've got 3 real zeros, but we can't have a 4th one, because if we did, it contradicts the structure of the derivative.
Yeah.
And the point is, that's it. So there's only these 3 real zeros. But by the fundamental theorem of algebra, we know that it can be factored over the complexes.
Yeah.
So the other 0 has to be complex. A pair of, and then since this is real, polynomial has to come in a conjugate pair.
So you're using the intermediate value theorem or the mean value theorem here?
I'm using the intermediate value theorem down here. The mean value theorem is what's see the mean value theorem?
Yeah, because I'm
Okay, so what's the mean value theorem? How to do any of this? Mean value theorem. If you apply the mean value theorem to here,
it tells you there's a f prime of c,
right? F prime of c.
like f
F of
minus f a over b minus a.
Uh-huh. So what happens when b and a, f of a and f of b are both 0?
F of a and f of b are both 0.
Mm-hmm.
F c 0.
Yeah, f prime of c has to be 0,
Yeah.
which is to say that there's a turning point.
Oh. Okay.
So the mean value theorem tells you the existence of the turning points, which in turn tells you that the derivative has to factor, you know.
Yeah.
So point. So we got 3 real zeros, and we've got 1 pair of complex zeros, right? So now we know what the roots look like, okay? So now we can start thinking about, we also know that there's a 5 cycle in the Galwa group, right? So there's also a pair of conjugate roots, right? So that means that the Galwa group has to, there's going to be a conjugation, complex conjugation is the Galwa automorphism here. Let's see here, as he says. Let me read his language for it. He says, since f of x has 2 complex roots which are not real, let tau denote the automorphism of complex conjugation in C. Since the coefficients of f of x are real, complex conjugation is a Q-fixing automorphism of the splitting field here, right? So complex conjugation is one of the automorphisms in the Galwa group. It has order 2. Because complex conjugation and complex conjugation is again the thing. So what's that say? Now we've got that the Galwa group contains a 5 cycle. It also contains a 2 cycle. And then the argument rests on group theory. If you have a 5 cycle together with any 2, a 2 cycle is also called a transposition. So a 5 cycle with any transposition, if you have both of those things in the group, it will generate S5. So, and S5 is known to not be solvable. Therefore, this guy right here cannot be solved by radicals. So, so next time, I will foolishly, next time I could spend an hour trying to prove the theorem 38, lemma 38 and 39, but I think what would be a much better use of our time is if I foolishly tried to unravel the formulas for like the cubic, right? I think that would be more interesting for us. But what do you think?
I don't know. That video of the cubic makes you kind of want to go through it, but like you're asking, like, what's more efficient of our time?
Well, I tell you, I will take a.
You're definitely the better judge of that.
Well, yeah, well, that's debatable, but I will take a group. I'll take a look at it, and I'll either next time we'll try to fill in the gap of the proof this time, or what's more likely is I will try to talk more about the different possibilities. First of all, like the different possibilities for Galwa groups. If you've got like order 2, order 3, order 4, what do the Galwa groups look like? I'm not going to get into the order 4 that much, though, because there's like 13 different ugly possibilities, and all of those rest on group theory that you're not comfortable with, so it's like it's not a good use of our time. But on the flip side of things, trying to understand a little bit more about how they got to this point of trying to solve the the fifth order problem. I think that's worth our time, understanding a little bit more of the history of some of that stuff that they did in that video by the Veritasium fellow. Man, that video I was showing.
Well, I saw that.
Yeah, because I really think that's something we should be teaching in algebra. Here, for the sake of completeness. See this proof. Why is it completing the square? It's that picture, So we'll try to look at the cubic version of this guy. So anyway, I think that's it for today. So.